That's why you say. I did when I used this in New York. Still, oh, okay. Well, nice.
Catcher?
Resna?
No.
You were a powerlifter though, right?
Yeah, I used to do powerlifting. Yeah. I'm retired now. Too many surgeries.
Yeah, let's hang on. Have we got the 5, 4, 3, 2, 1 yet? We live. Let's go.
Go for it. Great.
Hi, everyone.
Hello on the internet. Hello here. Harry Powell from Tiger Graph will give us a talk about graph analytics and the taxonomy of graph analytics. Looking forward to it.
Thank you very much. Good to be here. This talk is about trying to make sense of graph analytics. So I've been using graph for a while in business, right, at Barclays and then at Jaguar Land Rover in the UK. And I found that everyone got the idea of using a property graph. So I'm talking about property graphs here, right? Everyone got the idea of using property graphs for modeling data. Just made sense, right? You could see all these nodes and edges and things were related and you can code them. That made a whole lot of sense. But people found it hard then to say, okay, now I've got this data in this graph. What questions can I ask of it that I could not ask of a relational database? What is this? What is this thing? I mean, it makes sense, but how do I use it, right? And that's what this talk is about. Trying to give you some tools, right? This is experimental, right? I'm just throwing this out here. I find this useful, right? With the collective brain may decide that it's all wrong, and that's fine too, right? But I find this useful, and I just wanted to share it. Okay, conventional analytics, right? When you think about it, it's pretty rubbish, right? Apparently you don't use the word rubbish in America, but it's like trash or something. It's not rub, it's rubbish. It's great at observations. You know, you run it through, you run some aggregation through, margins have increased by X%, you know, okay, great. But context, is that good or bad, right? Conventional analytics is rubbish at that, right? You have to, you know, do some statistical thing, but does that really make sense? Causation, what's causing it to go up or down? Conventional analytics doesn't have any real answer to that, right? Because all your column of data, everything is equally useful, and correlation and causation is not the same sort of thing. An action, what can I do next? Right? I've observed something, thought about the context, I understand what the cause is, what do I do next? So many times analysts go to their boss and they go, boss, I've discovered this thing, something's gone up by 6%. So what? What do I do? Is that a good thing? Is it a bad thing, right? Has something caused it, or is it just random? Nothing. Conventional analytics pretty much just uses some kind of distributional approach, nearly always this distribution, by the way, that you'll all know, the bell curve, the Gaussian, right? For everything, right? And in fact, it doesn't really help, right? Graphs actually are pretty good at context, cause, and action, and that's perhaps where we'll come to, right? But I wanted to sort of set the scene for why you want to be using graphs for analytics, right? This is different, perhaps, than what people are talking about with semantic graph, right? This is about running algorithms, running analytics. Why are graphs interesting? Because you can get beyond simply thinking about an observation and looking at a distribution and doing some statistical thing. You can look at context, you can look at cause, and you can look at action using graphs in a way that you can't with conventional data structures. Okay, so a few preliminaries here. You're all graph people, so you'll all know that a graph is a pair of two sets, a set of nodes and a set of edges, where an edge is a pair effectively between nodes, right? Specifically, I guess, an edge needs to be a pair between two nodes, both of which are members of the set of nodes, right? If that's your thing, that's the way you might describe it. Nodes and edges is my picture. And then importantly about graph databases and graph analytics, we think of relationships edges as first-class citizens. You can't do exactly the same analytics on an edge as you can with a node for certain reasons that we'll come to, but you can treat it as a first-class citizen, right? You can do analytics on the edge as well as on the node, right? Again, that's beginning to be quite interesting because you can't do analytics on a join, right? That doesn't make sense, right? You can do analytics on edges. You can add them up, right? That's a good starting point. Nodes exist without edges. Edges do not exist without nodes, right? So the set of edges can be null, but the set of nodes, I guess, if that were null, you certainly couldn't have any edges, but it wouldn't be much of a graph, I guess. And then really crucially, in terms of thinking about analytics, all the information, right, about the relationships between nodes is encoded through first order connections, right? If there's no actual connection between nodes, then if you look at a node, everything you need to know about the relationship of that node to the rest of the world is encoded through those first order relationships and then taking steps on from there, right? So again, I guess what this is saying is, and it's not a complete thing, because I'm not a mathematician, but it's saying there's nothing extra about relationships that is not encoded in the edges you've got. Okay, a couple of other preliminaries. So you then start thinking about what is equivalence in a system like this, right? You know, your primitive operators in a system like this is saying, how do I know one thing is equal to another, right? That's your first thing. And it gets a little bit more complicated here because because of that thing about only for effectively all the information being coded in first order relationships, right? Then a subgraph, right, a subgraph can be characterized as a node, right? There's no reason why it can't be. You can just draw a circle around it and saying, as long as it has the connections out that are the same as the other connections, right? This is connection equivalence, right? As long as it has the same connections, the same sorts of nodes, right? Then this subgraph can be characterized as a single node. And anything I'm talking about in terms of analytics with nodes can be applied to subgraphs, assuming you can compute them. So that's why what we might, sorry, I'll start again. I'm getting ahead of myself. Okay, equivalence. Think of equivalence as two things, right? When you're just thinking about relational databases, equivalence is one number equal to another, right? Here, we can be interested either in the content, right, of the properties, the aggregate properties of two subgraphs or two nodes, whatever it is, right? Or we can be interested in the way that those nodes connect into the graph, right? Things can be equivalent in both of those two ways. And if something is kind of hard equivalent, like fully equivalent, then it's equivalent both in terms of its content and the way it connects into the graph, right? Those two things would be exactly equal, but sometimes you're interested just in one thing, in the edges nature of it, all right? And sometimes you're interested in the node nature of it, right? And I just added below, hard equivalence is exact matching of two subgraphs or two nodes. Is this thing exactly the same as this, right? Whereas soft equivalence, sometimes we're simply interested in analytics in some subset of the attributes of a subgraph or a node, right? That's what I've called soft equivalence, right? But most of this comes from the idea that the informational content of one node the relationship information that you can think about with a node, right, comes simply through the connections into it, not through anything further than that. Okay, so just a couple of preliminaries. And one more, right? So I'm introducing these things a little bit quick. I'll give you the slides afterwards to the extent you haven't thrown rotten tomatoes at me and tell me I'm speaking nonsense, right? One of the most interesting things about property graphs is that compared to the relational database world, where people use the term similarity and distance actually in a very interchangeable way, right? So people say, you know, the similarity between something can be expressed as a Euclidean distance. Like we've immediately mixed up similarity and distance, right? Here, similarity is actually different to distance. Similarity is about the content, right, between nodes, right? Whereas distance is actually about the connection between nodes. So again, we're kind of, when you start thinking about this world, you need to start disaggregating the connections from the content, right? And as you and that then gives you more tools to work with, right? Sometimes you combine them, sometimes you keep them apart. Okay, this is my taxonomy. This, I think, is the abstraction of the questions you can ask of a graph, right? And we'll go on to I've got slides on each one of these, bad luck. And I've got examples from industry of the kind of questions you can ask for each one of these, right? But what I want you to think about is, and I may be wrong, right? If I'm wrong, that's cool as well, right? But as the way I'm thinking about it is that there are effectively 4 pairs of question types in each of those columns. Don't do your head in too much about it so far. One seems to have some sort of edge nature to it. One seems to have some kind of node nature to it, right? And again, we'll come to that. But you can see that this is not fully complete and thought through and mathematically proved. I'm just throwing it out there. I find this really helpful. I use this in my daily work, and I find it helpful. And you move from quite primitive analytics here. These are basically your primitives, right? Is one thing connected to something else? Is one thing equivalent to something else? Remember, when you see a node there, it could be a subgraph, right? Through to some more complex stuff down here. But effectively, this is your primitive, right? These two are effectively right angles, one to the other, translations of one to the other. I hate this. I'm going to change it because it doesn't. We've talked about subgraphs being the same as nodes, so it doesn't actually need little subgraphs in there. It could be nodes, right? But this is about, you start off at 2 nodes and try and find a common ancestor. This is about, you start off 1 node and you try and find an alternative action through 2 intermediaries. Effectively, it's the same thing but rotated. Here, we're talking about commonalities between 2 nodes, where one is about trying to introduce a missing edge and one is about trying to remove a duplicate node. So it's nodey and edgy. Obviously, it doesn't make a lot of sense to introduce a node out of this kind of analytics, right? Because that's creating new information in the same way. Sorry, let me keep going. And this final column is about groups, right? How do things relate to groups, right? So we'll kind of go through this. But this is, I've scratched my head about this quite a lot, and it seems to work. But let's go through some specifics, right? I recognize I'm sort of going quite quickly, and I want to make sure we spend some time on each one of these. Okay. So these are your primitive. This is your first of your primitives. Is one thing connected somehow to another, or is it not connected? I guess not connected is the opposite of connected. Perhaps it's redundant to talk about not connected, right? And just to give you the, I hope you like the shading. I'm from Tigergraph, by the way. Orange is our color. You'll see lots of orange and blue in there. That's our corporate thing. I won't talk about Tigergraph again, but if you want the best, that's us. We'll leave it with that. Okay. We start at an orange node, and sometimes we finish at a blue node, right? So in order to do a query where we're trying to understand whether one thing is connected to another, we need to know 2 nodes, start and end, and these whitey gray nodes are just kind of representative of any node you need to traverse through, okay? So I'm guessing that I'm probably not going to have a whole load of conversations about this one, but actually these are really useful. Simply knowing if one thing is connected to another, right, is your starting point for all graph analytics, right? In finance, we might say, is an account connected to a known fraudulent account? That's a pretty big thing, right? That's worth £100 million to, you know, JP Morgan or something like that, right? It's $100 million, actually, probably. Manufacturing. When we change a part, what other parts are affected and should be checked? Really, really important part of design, right? I change something, how does it affect the rest of the network? Telecoms. If there is a bandwidth problem, where's the bottleneck, right? Is it this or is it that? Where are we? What things are connected? How's that going to be effective? But I want you to go back and say, okay, each time we revisit another one of these archetypes that I think are archetypes, right? We're going to be saying, okay, how do we convert that into the real world, right? And is that something that is unique to the graph world, or is that just graph people trying to make it more exciting than it actually is? Okay, this is the other of our primitives, equivalence. We've talked about that. Are these 2 things content equivalent? You don't necessarily need to have any linkage between them. It's just simply a search function. But remember, it can be interesting in a graph because is it well, I said content equivalent. It could be connection equivalent, right? We're just simply searching through to see whether nodes have the same connections into them, have the same content in them, and whether they have either one or both. That's our primitive for doing that kind of thing. But again, there's quite a lot of interesting questions you can ask simply with this, right? So in manufacturing, could two different clusters of parts effectively be interchangeable? That's a subgraph thing, right? You may define a feature in a motor car, I came from the motor car industry, as 3 parts in one of your models and 5 parts in another. Not for any good reason, but 2 different engineers engineered them. How do you search through your database and try and find those little bundles that are equivalent between them, right? So that you might be able to change, you might be able to standardize on one. Really hard in a relational database to try and work out whether 5 parts here and 3 parts are there. But in fact, if something is content equivalent and connection equivalent, you can swap it, right? That's sort of interesting. 2 subsections of a comms network, functionally the same, doing the same thing. Retail. Amazon can't deliver you a bundled product of some kind. Can it find a combination of products which are equivalent functionally to the thing you wanted to buy? Again, really hard, right? Actually quite easy with a graph. And again, it's just a primitive, right? But it's a primitive because we've decided that because all the information about a subgraph comes in through its connections, you can draw a ring around a subgraph and call it a node. I hope some of this is making sense. Okay, we're on to something a bit more exciting here. This is actually really exciting, right? Because one of the things I said to begin with was conventional analytics was a bit rubbish, right? Because it couldn't think about cause and effect, right? And that's because you can actually, right? Those of you who are fans of Judea Pearl and causal inference and all that, how does he do it? He puts it into a graph. Why? Because you're effectively restricting your model, placing restrictions on your model based on your a priori knowledge, to say, this is kind of how the world works. Now let's see if there's a connection. Now, TigerGraph is not specifically a probabilistic graphical model, right? But given it's Turing complete, I guess you could code that if you really wanted to. The point here is, because you have the structure, you can start thinking about, if I start off with 2 nodes, right? Can I find the common ancestor or successor? Actually, ancestor or successor is only in your mind. It's not in the mind of the graph. The graph doesn't necessarily have direction in that sense. But it's really, really interesting if you're in the finance industry, right? And you want to know, are two graphs or subgraphs connected effectively to the same thing above? Really, really important in anti-money laundering. Pretty hard to do in a relational database, particularly because you don't know how many jumps up you have to go. And it won't be the same number of jumps for both sides. You'd kill yourself trying to do that. But actually, it's a relatively natural thing to do in a graph. 2-part, classic, quality, right? You want to think about quality. You have 2 parts failing. Is there a common root cause between them, right? That is this structure completely, right? Again, very, very difficult to do without it. And you can then layer statistics on top of it. What we did at JLR was that we had a number of, what you can do is you can reduce the number of blue dots to a feasible set, right? You can say, these are the culprits. These are the potential culprits. Now let's run statistics on them. Much better than just going, I'm going to run statistics on everything and run it over and see what, where I come in a bell curve and all of that, right? You reduce it to context. We talked about context, right? You say, the context is we've got 10 potential problems. Right, and I've got some cool slides that I'm not doing today about that. But that actually can be quite interesting, the way that your feasible set can be a very large number of different kinds of nodes. But by reducing it to that, you can then focus on that. So quality is a really big issue here, hard to do outside. 2 products have changed in the amount of sales. What kind of common nodes are there that perhaps are driving that? Again, you probably want to do statistics after you've narrowed it down with a graph, but without doing that, a lot of graph analytics is about partitioning, right? I have a huge amount of data, right? If I try and run statistics over all my data, just a list or a table, I kind of run out, firstly, I run out of computation. Secondly, I'm unable to get really rich information because I'm having to effectively spread it so thinly, right? Here, you can use a graph to work out what your search space is, right? That's effectively what we're doing here. We're finding a bunch of blue nodes and saying, restrict your analytics to those, because it's one of those guys, right? We know that from the structure. We know in our manufacturing bill of materials that it can only be parts that are connected to it, or processes that are connected to it, or engineers that worked on it. An engineer that never worked on this part can't be responsible for it. But once we've narrowed it down, we can then run our statistics. Okay. Now, the other side of this, and I hate this because it's my fault, but really imagine there's one blue node, one orange node there and one blue node there, because we know that nodes and subgraphs are equivalent if they want to be, right? This is something the way we made tens of millions of pounds with this thing at JLR, right? And it's kind of like, you can see how it's kind of like the brother to this one, right? It's a very similar structure. This is, if you remove a node, let's imagine we take this node and we remove it, right? Can we find the closest alternative in our structure that is content and connection equivalent, right? And if it's not content and connection equivalent, in this case, it needs to be connection equivalent and soft content equivalent, as close as possible to in terms of content, but still links into the graph the same way, right? This is a multi-million dollar query, right? So in manufacturing, a part is unavailable, and that means I need to shut my factory or something because I can't deliver it. What is the closest, in my order bank, what's the closest thing I can find, right, that uses all the parts that I've already got in to deliver the first, product, but doesn't include the thing that's not available? It's actually really hard to do that in a complex manufacturing environment. Graphs do it quite naturally. In fact, the story I tell, Alice, who was in my team at JLR, the problem came up, similar sort of problem. It was a problem we'd never really been able to answer before. She, during the meeting, started working on the graph database, of which, you can work out which one it was. Within 45 minutes, she had the query that answered the problem, right? Made us about £7.5 million, that one decision. Right? And it's because this happens really naturally in a graph, right? But also you might want to be thinking about mitigation strategies. You know, if one thing can't happen, what can I do instead? Action is so important to a graph, right? And I know I'm not spending enough time on the shape. Maybe people need to spend a bit more time afterwards if they're interested in thinking about that. And then, I am sort of on time, actually. Maybe I've got some time for questions or moving back in a second. The last pair of nodes, we've been through the primitives, kind of equivalence and pattern matching. We've been through these kind of, oh no, I've actually got a bit more than that. Right. Yeah, I'm probably on time. Okay. So this is about how two nodes might relate to each other through the things that they share in common, right? And this is kind of interesting because in some sense, again, it's about reducing the search space. If you have two things that you want to compare in the non-graph world, you'd need to compare an enormous amount of things about them, right, in a lot of different complex kind of ways before you can know whether they're close to one another or not, right? So imagine that I want to do cosine similarity, right, I want to find the thing that's closest to, I've got a node, and I'll find the thing that's closest to it in the rest of the database. So I need to do effectively, if the number of terms is n, it's n comparisons in order to do that, because you've got a huge search space. A graph naturally reduces the search space to everything in the context around the node that's in question, right? And so comparison is really interesting. Comparison of attributes, comparison of connections, that kind of stuff is really interesting. We use it really for two things. One is, if two things have a lot of things in common, might they actually be the same node? In which case, it's like a deduplication question. It's a, can I remove this node? Because actually they're basically the same thing, right? The alternative is almost exactly the same thing. It's like if two things share lots of things in common, right? Should there actually be an extra connection? One is about removing a node. One's about introducing a new edge, right? They're basically the same question, but they're actually they come up with quite different things you use them for, right? So conceptually quite similar. Yeah, 4 minutes, I know. Terrible. Here we're talking about finance. Our two products the same. Classically in customer 360, two customers basically the same. They're using the same devices. They kind of live in the same house. Are they actually the same person, right? The adding edges one, for example, quite real-time recommendation, right? So recommendation in a graph is the sister of Customer 360. It's kind of like the upside down version of Customer 360. One involves removing a node, the other involves introducing an edge. And then finally, because I wouldn't want to come over time and I have 3 minutes, the final pair is about groups, right? So you can actually see that maybe we don't have 4 pairs, we have 2 pairs of pairs, right? Because you can see the pictorially quite similar between the two. Of course, I've drawn them in that way, so maybe I'm cheating, right? But this is about groups. And fundamentally, you can do 2 things with groups, right? You can say, can I take some data and cut it into 2 groups, right? Or given I have a group, is this a member of it or not? Or no, given I have a group, where does this node sit within that group? So this is about partition. Is a node more connected to group A or to group B? I have a node, I have 2 groups, which side does it fall into, right? And the comparison, I'll just hop back to this in a second. The comparison is, I have a node, or I have a group, right? What best characterizes that group? So one is like, I have a node, do I put it into a group or not, right? The other one is, I've got a group, how do I characterize something within that? So partition, big questions around partition are a big thing we did at Barclays. How is one business customer performing compared to other similar customers, right? That was a really cool thing, right? You want to be able to advise our customers, and we were observing things about our customers. The number of people walking into a shop has gone up or down. How does that compare to other, I don't know, barbers in that part of town, right? Because you get context and because you can partition information very easily in a graph, that's a really interesting thing to say. And within telecoms, you're really interested in partitioning up your group, your communities into people that communicate or share things in common. So partition, I think, is fairly straightforward. And influence, again, I'm kind of coming to the end of my time, but influence, we're kind of interested in people who are members of groups, but what member of that group is perhaps typical of it, right? So centrality might be one method of that, one method of ascribing a number to that, right? Calibrating that. But it's not the same thing, right? So I'm kind of out of time. I thought I'd leave you with that. We probably won't have time to answer questions, but I will be around for 2 days. I'd love to have conversations with you. Have a think about this. If you think it's rubbish, say so. That's cool, right? If you think it's useful, go and use it. I'll share the slides because I find it useful. I find it useful, and sometimes things are wrong and useful. Okay, fair enough. I find it useful, and I'd love to talk to you more about this. I'm trying to make sense of it.
Have you uploaded your slides on Zenodo, the platform where we upload the slides? So you will very soon do it. Also, are you on the Slack space?
Could be.
Conversation continues on Slack. If you're online, you want to ask questions or here.
I'm here.
Larry, and I'm sure.
Yeah. And it doesn't need to be a conversation about Tiger Graph, although it will be a better one if it is.